In this video, we will discuss a new optimization algorithm, that is red fox optimization algorithm. This algorithm is inspired by the hunting behavior of red foxes. So this algorithm simulates how red foxes search for the prey and how they hunt. So here we have topics covered in this video. What is this algorithm all about? The main inspiration behind this algorithm and all. Then we will discuss few facts about red foxes, because the main inspiration behind this algorithm is the hunting behavior of the red foxes in real life. Then we have different mathematical models. So these mathematical models are used to simulate different hunting strategies used by red foxes in the real life. Then step by step we will try to understand how this algorithm is working. And the last we have the application. So first you can see here this algorithm is introduced in 2020. And the main inspiration behind this algorithm is the red fox's hunting behavior. This algorithm also simulates how red foxes search for food and hunt. So it is clear red fox hunting behavior plus their hunting strategies are simulated in this algorithm to find out the optimal solution for the optimization problems. Now we will discuss few facts about red foxes, because the inspiration behind this algorithm is their hunting strategies, their real life behavior and other. So first we will discuss few facts about red foxes so that we can easily understand this algorithm. Red foxes are highly adaptable and they can survive in various environments including forest, grasslands, mountains, deserts, even in the urban areas. So you can see they can be easily found in North America, Europe, Asia, North Africa. About size you can see here. Adult red fox body length is up to 45 to 90 centimeter. Weight, it is in between 3 to 14 kilogram. In the lifespan we have 2 to 5 years and they live longer in the captivity. And their diet include small mammals, birds, their eggs, insects, fruits and vegetables. Like other meta-heuristic algorithms, in red fox optimization algorithm, again we have local search and the global search. All search agents will move according to local and the global movement. So in this algorithm, to search better position, all search agents will move according to local and global movements. The algorithm simulates different red foxes real life behavior. So in this algorithm we use different mathematical models inspired by the red foxes behavior in real life, like how red foxes search for the food, how they hunt, reproduction. This algorithm simulates these different mathematical models to find out the optimal solution for any optimization problem, like their food search, how they search for the food in real life, and how they hunt for the prey, reproduction, and how they hide from the hunter. So here you can see we have 4 red foxes behavior. They are simulated in this algorithm, and for that we will use different mathematical models for food search, for hunting, reproduction and hiding from the hunters. So here you can see different steps are used in this algorithm. First we will initialize all the important parameters. Here we will initialize the algorithm parameters plus the optimization problem parameters. Done. After that we will initialize the population. So we have the virtual environment, virtual foxes, that is the search agents. So we will initialize any number of populations that step by step we will discuss further. Now we will start here the loop. Define the coefficient. For each fox we will calculate the fitness value using objective function. Then we will calculate here individuals, relocation. Then define the noticing the hunting fox. It means what if the fox is noticed by the target, then what to do. Then we will sort the population based on their fitness values, and then we will remove the worse foxes. So it is considered that the worse fox is either killed by the hunter or they leave the herd. Now you can see we remove the worse foxes. So here we need to balance the population. So we will replace the new foxes, increment the counter, then repeat the loop until the stopping criteria is met. And when the stopping condition is met, we'll stop and display the best solution that you found in the last iteration. So first step, we have parameter initialization phase. Here you can initialize different objective function parameters, algorithm parameters, and other. So first we have population size. That is the total number of search agents you want to use. Here this value can be 100, 500, 1000, it depends. After that we have current iteration, maximum iteration. Then we have Fox observation angle that is used in the mathematical model, weather condition, theta. This is also used in the mathematical model. So here we are using different mathematical models to simulate red fox's behavior. So here define the parameters. Then you can define here your objective function, or according to your optimization problem you can define here. Then we have design variables, or you can say dimension. Second, we will initialize the population. It is clear that we have here the virtual environment, virtual red foxes as the search agents. So here for each fox, each fox represents a potential solution to your optimization problem. So we'll consider here each fox as a point. Here you can define any number for the population. Value for n can be 1, 2, 3, 400, 100, 500, 1000, other. And here small I, that is the number of foxes in the current population. J, that is the dimension, or you can say the total number of design variables. Small t, that is the current iteration. After that here f, that is the objective function that we will apply on the current population on each fox, and we will calculate the fitness value for each fox in the current population. That we will calculate in the upcoming step. So first we will initialize the population. Here you can define any number of red foxes, and then we have the number of design variables or the dimension. After that we will start this. We will check whether the current iteration is less than or equal to the maximum iteration or not. Right now it is 1. Right now current iteration is 1, and the maximum iteration, suppose we have 100, suppose it is 1000. So right now the condition is true, so we will move to the next step, and in the end we will increment the counter, and we will keep incrementing the counter until the stopping criteria is met here. And once this stopping condition is met, we will stop and display the best solution. Next we will define the coefficients. Here we have one coefficient, that is alpha. This is the scaling parameter, and we will set this parameter only once in the iteration for all individuals in the current population. So this parameter is basically used to model the randomly changing distance from the prey during fox approaching. So here when the fox is approaching the prey, this parameter is used to model the random changes in the distance between fox and the prey, that is the target. After that, for each fox in the current population, calculate fitness values. So here you can use your objective function that is declared according to your optimization problem. So we will apply the objective function on the current population on each individual. So here we have two cases, either we are doing the minimization or we are doing here the maximization. Accordingly, we will calculate the fitness values, then select the best individual among all. Here if you are doing the minimization, then we will select the minimum value among all as the best, and if you are doing the maximization, then we will consider the maximum value among all as the best value. After that, we will calculate here individual relocation. You know how red foxes hunt. Red foxes are skilled and clever hunters. They use a variety of techniques to capture their prey. And red foxes are intelligent, and about red foxes we know they are intelligent, fast reaction, sharp senses, all play important role in their hunting. Now you can see this is the red fox, and here you can see prey location, and around this target you can see we have different possible location where red fox can move. So here we will calculate the individual relocation. So here we are using different mathematical models to simulate this behavior. In this algorithm, the exploration of the surrounding land is modeled using the objective function values. So it is assumed that the best individual, that is the best agent, has explored most interesting land, and they can share this information with other. So first we will sort this population according to their fitness condition, and for best candidate they will calculate. So first we will sort the population, then for the best candidate you can see here x best, that is the best individual, or you can say best candidate, best member, best fox among all. So for the best candidate we will calculate here the square of the Euclidean distance to each individual in the current population. Here you can see the square of Euclidean distance that is calculated for the each individual in the current population. Done. Here we have virtual environment, virtual red foxes. So this is virtual search space. So it is assumed that the best individual among all in the population has visited the most interested land, and this individual can share this knowledge with other family members, that is the other search agents. So now we have best search agent, and then we have other search agents. Suppose the best agent find out interesting land where there is a lot of food. Now this agent will share this information with the other individuals. So in order to simulate this behavior, we are using this mathematical model. After that, we will move the individual in the population toward the best one. In this algorithm, we are trying to find out the optimal solution. Suppose if one candidate, that is the best candidate, best solution, done. So we will move other candidates, that is the other solution, near the best solution. You can see this alpha, this is hyperparameter, also called scaling parameter. This is also set only once in the iteration for each individual. Done. So in this step we calculated the individual relocation. Now we will move the foxes. So here we will check if the fitness value of the new position after they move toward the best location. If the new positions are not better, then we will return the fox to the previous position, because we need the best solution. Suppose we have an individual whose fitness value before is better than the new fitness value, so we will consider the older one, not the new one. So here we will check the all individuals new position fitness value, and then we will decide whether we will move the fox or we will return the fox to the previous position. So in the real life, when they are searching for the food, sometimes they come home without food when the hunt is not successful. So here this is simulated. After that we will define the noticing the hunting fox. Now here we have another scenario. Suppose red fox is hunting a target. What if the red fox is noticed by the target that I'm going to attack by the. So here this behavior is simulated. Now what if the hunting fox is noticed by the target? So we know the red fox hunt throughout its entire territory, and in case when the prey is spotted, fox will try to move closer quietly without noticed by the prey. So that foxes are clever, we know. They play different tricks around the target to make them believe that fox is not interested in hunt, and when they move closer to the prey, they attack as fast as possible. That is surprise attack. So here this behavior is simulated. In order to simulate this behavior, we will use a random value, that is mu. You can see here this value is in between 0 and 1. So this is the random value that is used here. So this is used to denote the possibility of fox being noticed by the prey during hunt. This value is also set only once in the iteration for all individuals. So here you can see if the fox is not noticed, then we will calculate the fox observation radius, then we calculate the relocation, else fox will stay at its position, no movement. Now we have the mathematical model for this. In case, so first case we have when the fox is not noticed by the target, so we will calculate the fox observation radius r. You can see when we will initialize the parameters, we will initialize this fox observation angle already that is used in this mathematical model. Here you can see we are using this parameter here. So we set this parameter before. The value for this we have it means 0 and 2 pi. So here two parameters are used for the fox movement observation radius. First we have the value for alpha, that is between 0 and 0.2. This is the scaling parameter set only once for all individual in the iteration. Using this to model the distance between the fox and the target. Next parameter we have this one, phi naught, that already we declare before, that is the fox observation parameter. This value we have 0 in between 0 to 2 pi. This is selected for all individuals at the beginning of the algorithm to model fox observation angle. So here you can see this equation how we can define Bayesian radius of hunting fox using this equation. This is the theta, that is the random value between 0 and 1. So this theta value is used to represent the effect of bad weather condition to remain alert for any possible danger like fog, rain. So this movement is modeled using the system of equation for the spatial coordinates. So how we can calculate the relocation? Here you can see we have the angular values and every point has a randomly assigned value according to phi 1, phi 2 up to phi n minus 1 that belongs to 0 to pi. So you can see this model, it simulates the behavior of fox that discover a victim, that is a prey, and the fox is trying to move as close as possible to attack. This is the first case. Now second case, when the fox is unsuccessful, it is spotted by the target, fox is noticed by the target. So here fox will try to approach another target in the same way. After that, we sort the population based on their fitness values, and suppose we have different fitness values. Now if we are doing the minimization, according to the minimum value we will sort them, and when we are doing the maximization, then accordingly we sort the population. After that, we will assume that worst solution, that is here the worst foxes, either they are killed or they leave the herd. So here based on their fitness value, either we will kill the foxes or we will make them leave the herd. So here suppose we are doing the minimization and we need the minimum values only. So right now again this you can see here we have two maximum values. Remove these values. So it is assumed here. So this is used to simulate in real life whether the fox is killed by the hunter or they leave the herd and now they are moving solitary or they will make their own group. In order to simulate this behavior, we will select 5% worst individual from the population according to their fitness values for the each iteration. So here if you are doing the minimization, then we will remove the maximum values. If you are doing the maximization, then we will neglect the minimum values. So right now suppose we are doing the minimization, so we will not take the maximum values. So here we will consider that either these individuals are killed or they leave the herd. So it is assumed here that the removed foxes either they are killed by the hunter or they migrate to the other places. Done. Now we will replace the new foxes. Why? Because we need to balance the population. So as we do the worst solution from the population, now we need to balance the population So we will replace them with the new individuals, that is the new solutions. Now how we will generate new solutions? Now here we have two cases. Now when we are doing the replacement of the new individuals, we have here two cases. Either the new individual is a nomadic individual or it is the reproduction of the alpha couple. So in the first case, it is assumed that the new family member become migratory fox and move outside of the area in search of food and chances to reproduce within their herd. So here the random places are chosen from the search space individually in the habitat. Second case, the reproduction from the alpha couple. Here in this case, we will select here one alpha couple. So here in this scenario, in the second scenario, it is assumed that the new individual come from the alpha couple. Here you can see we have two best individual. They are reproduced and they combine into a new individual. So calculate the center of habitat. After that, we will calculate the square of Euclidean distance for the alpha couple. And after that, we'll perform here reproduction. We will increment the counter. Then we will check the stopping criteria and then we'll display the best solution when the stopping condition is met. So about application of this algorithm, we can use this algorithm for complex multimodal problems where the traditional methods either fails or they are slow, and we can also use to solve a number of optimization problems because it provides efficient results in comparison with a number of optimization algorithms. So here we discussed the red fox optimization algorithm. For more details, you can check the research paper and you can check everything in detail. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.